Stephen F. Austin High School in Fort Bend. And I'm going to be an undergraduate at University of Texas at Arlington this fall. So woo, go Mavs! And so my project this summer, I worked, of course, under Dr. Reimer. And my project this summer was tuning the activity of nanoporous zeolite from hierarchical designs to bifunctional catalysts. So to start off, you all are probably thinking, what even is a zeolite, okay? What is a zeolite? That's the first thing we're gonna go over. The second thing that we're gonna go over is what did I do? And the third, of course, is final remarks, thank yous, and conclusion. So there's a lot of words here, but essentially what I wanted to say was I participated in this program last year, and because I had such an amazing experience, I came back for more. And this year I interned, once again, in Dr. Reimer's lab group at the main campus in the Department of Chemical and Biomolecular Engineering. And to jump into it, so what is a zeolite? A zeolite is essentially and generally a crystalline structure that is made up of tetrahedrally coordinated aluminum, silicon, and oxygen. And so essentially silicon on its own has a 4+ charge and wants to grab 4 other oxygens. But when you incorporate aluminum into the framework, because the aluminum has a 3+ charge, it leaves 1 charge that wants to be filled. And that, as you can see in the blue part of that, is the Bronsted acid site, or what we call like a Bronsted acid. And so zeolites can grow just like how, so zeolites of course are crystals, and crystals can grow in a couple of different directions, but zeolites specifically can grow in 3 dimensions as illustrated by the picture. They can grow in 1 dimension, 2 dimensions, or 3 dimensions in multiple different ways. So when I say that they can grow in multiple different ways, these are just some of the ways that they can actually grow. They don't just look like a regular crystal that you crack open in one of those National Geographic kits. And so there are almost over 250 recorded zeolite frameworks. And so as the molecules and atoms coordinate tetrahedrally, they create pores. And so of course the pores make up the framework, and there are over 250 frameworks that are recorded. So specifically my project will be focused on the MWW type framework, and as you can see in the picture a little bit to the right, you can see that it's 2D layered, and that's essentially what we're focused on, is layer separation and pushing the layers open as much as possible so that we have access to the Bronsted acid sites. And so of course a zeolite grows, but what does it grow around? As you can see on the blue circles are what we call organic directing agents, or OSDAs. And so that essentially gives the atoms something to mold themselves around as they grow. So next, what is a surfactant? This is going to tie into the next slide, but a surfactant is essentially a molecule that has a polar nitrogen head that's hydrophilic and a non-polar carbon-based tail that is hydrophobic. And so as I mentioned before, that 1 proton and charge that wants to be filled, it interacts with the surfactant because the head of the surfactant kind of is introduced into the framework and fits itself literally into the layers of the zeolite and pushes it apart. And so that's what we call, after the OSDA is burned off, that's what we call delamination. So once again, a bunch of words right here. Essentially my project was manufacturing certain surfactants to push apart the zeolite and also create the framework at the same time. And so what we did in my project specifically, we first tested certain surfactants. So in the blue, that column over to the left, these are all of the surfactants that were tested by the time I got there. And then the ones that are highlighted, surfactants 1 and 2, were ones that successfully crystallized the zeolite framework. And then in the green text, you can see that indicated by the asterisk and the and the picture in the left corner, the head of the surfactants that crystallize the zeolite framework were replaced with the surfactant. And so we just wanted to kind of test that to see, okay, because we have something that we know can actually build the framework, can we combine it with something that has successfully crystallized the framework to do both at the same time? And so the first surfactant, as you can see, surfactant 1, is a 16 single carbon chain with a pyridinium head, which is a big word, but that's just kind of the molecular structure of it. And then the second surfactant is a single ether chain, which means it includes oxygen in the tail, and it has a tetramethyl ammonium cation head group, which is a mouthful. And so surfactants 3 and 4 are essentially based off of surfactants 1 and 2. So as you can see, indicated with the purple highlights, the number 3 is based off of number 1, and number 4 is based off of number 2. And of course, they're just the head groups were attached to the surfactant. And as you can see, kind of in the right side, that's a close-up look of what the surfactants look like. They can come in many different powders. They can come a little bit sticky. They can come in many different ways. And so I guess you're all wondering the big question, did the experiment work? No. So the short answer is no, but the long answer is one of the first characterization techniques that we use is called XRD, and it's the long name is X-ray diffraction, and it's essentially you take a sample and you use a laser and you shoot it at one angle, and then one of the receptors, it receives that transmission. So you're shooting it here, 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 and it's receiving it from all of these different angles. And as you shoot it from all of the different angles, you can see, okay, where does the framework show up? So it's kind of like when you put your hand in one of those things at like the playground and you see your hand on the imprint. If I were to put a rod there, you wouldn't see the same thing as my hand. So that's kind of what this graph is. As it shows up at certain peaks, that indicates a certain framework because the bonds and the rods are at a certain place. And so as you can see kind of in the bottom two, if you get a wave, then it's amorphous, which means it hasn't crystallized. So as you can see, it didn't work. And so yeah, why do we think this happened? Honestly, the reason why we can assume that this happened is because of the tail. So obviously the OSDA, we know, can actually create the zeolite and crystallize it. So the only other option is the tail. So there's definitely been a lot of new experience. These are just based off of some of the ones that I initially worked with when I first got into the lab. But as I've been here for the last about 4 weeks, there have been a number of new experiences that have crystallized, some have not. And so as we gain more information, we just are able to, figure out what works, what doesn't, what ratios, and things like that. And so when you combine the OSDA and the surfactant, you essentially make a bifunctional surfactant, which is kind of the bifunctional aspect of my assignment. Okay, next one. And so, of course, thank you to Dr. Reimer. Thank you to my mentor who's here, Amir. Thank you to Annabelle, I don't think she's here, but who was my partner essentially. And then thank you to Dr. Monica. Thank you to Mr. Edgar Terizo, and everybody else that I met from the Reimer group. For the rest of my life, I'll literally never forget the research that I did here. I've learned so much, and I want to thank Dr. M.A. for helping me jump back in. I want to thank Aunt Carolyn Burnley, my just for helping me, mentoring me, and recommending me for this program. And yeah, just everybody else that I met. Thank you guys.